All right. Well, welcome everybody to today's STEM talk. So we are very happy to have David Shih here as our speaker today. So David is from Rutgers University, where he's a professor at the New Energy Theory Center and also at the Department of Physics and Astronomy. So his background is actually in theoretical physics, but in recent times he has been doing a lot of exciting work on machine learning and AI for fundamental physics. And what he basically does is that he develops various exciting methods for working with large data sets from particle colliders and various astrophysics observations. So in terms of physics, he works on things like dark matter, stellar streams, beyond stellar model physics, and other kinds of new physics searches. But then in terms of machine learning, the kind of tools he uses and develops for those things involve a whole like a range of techniques from generative models to anomaly detection, fairness, feature selection, interpretability, and many other things that many of us are very excited about. So with that today, what he will be talking to us about is searching for the unexpected from colliders to start with modern machine learning. So, David, please take it away.
Okay, thanks very much for the invitation. It's a real pleasure to be here. I was just saying at lunch, the STAMPS Center, it seems fantastic, and I would kill for one of these at Rutgers. So I really mean it. Okay, so yeah, I wanted to talk to you today about just, I was going to focus sort of on one of the things that I'm working on, which is maybe the thing I'm most passionate about, which is searching for anomalies in the data. And I'll be talking about how we're developing techniques to do this kind of anomaly detection motivated by LHC searches, and then also finding ways to port those over to astronomy data to look for interesting objects there. Okay, so you can't start a talk on AI and physics without mentioning this year's Nobel Prize. I thought it was a great chance for our field to grab some more turf, maybe. No, but so yeah, so I think at least one of them was a former physicist. And this highlights, I think, the importance or tight connections between physics and machine learning. And in this case, I think it was mainly a prize about applications of physics to machine learning. And maybe someday we'll have a prize for applications of machine learning to physics. Okay, and of course, we're all here in part because there's been a revolution going on. And that revolution has been driven in large part by some remarkable techniques being developed, largely in industry, all revolving around this thing called generative AI. And so there's been a lot of hype about it and a lot of news. And also it's driving, I think, a real growth in interest and activity in my field, so high energy physics. So machine learning in high energy physics has been sort of on an exponential rise. Sort of starting, I mean, in the very early days, there were some highly influential papers, and particle physics is actually one of the early adopters of many machine learning techniques. But the sort of modern revolution, I would point to somewhere around here, really taking off 2016 or so, which is sort of like a few years after the revolution started, I guess, in industry and CS. So, but we're rapidly catching up, and there's a lot of activity going on. A lot of people, I think, are getting more and more interested in these techniques. But the first thing, this does breed some kind of anxiety, I feel like. And so the first thing I think a lot of people ask me in one form or another when I tell them what I work on in high energy physics, is, you know, in one form or another, it's will ML eventually, or AI, eventually take my job? So, you know, this being sort of a general colloquium, I thought it's good to start off with some jokes. So I asked ChatGPT this question. I said, I'm a particle physicist. Will AI take my job? And it gave me a very long-winded answer. But actually, there's a lot of good nuggets in there, and a lot of it is what I would say too. So it's going to help, you know, obviously it's going to help analyze large data sets. It's going to improve simulation and modeling. It can improve experimental design. Fortunately, it won't replace theorists. I'm a theorist by training. The creative and abstract thinking required for developing fundamental theories still remains a domain of human scientists. So there you have it from the AI. It's not going to take our jobs, right? It promises. Yeah. But yeah, I think this is a key point. So AI is a tool that can augment the work that we do, and it can handle large amounts of data and accelerate discoveries. And so, embracing this new tool and developing the skills that help develop it further and apply it to our data in interesting ways, that's sort of going to be the new direction. Okay, I thought this was way too long-winded though, so I also asked it the same question, but please answer concisely. Will AI take my job? And this was the answer. So there's like the ghost of Dirac is in there. People understand the reference. Yeah. Okay. All right. So that's all out of the way. So what is all the hype really about? I think the thing that excites me about modern machine learning and applying it to our kind of data is that I view it kind of like a telescope, but for data. So I think of it as allowing us a new kind of instrumentation, which allows us to see further into the data. So instead of further into the cosmos directly, or microscopes looking into the biological world, this is now like a telescope, an instrument that uncovers a new level of understanding and complexity of the data itself. So that's how I think about it. And that's what excites me. And just like any major new instrument that's been invented has basically led to super low-hanging fruit. Like Galileo can just point his thing up at the sky and discover moons of Jupiter. So it's once you uncover a new layer of something you can observe using a new instrument, it just opens up a huge territory for discovery. That's what I think is really exciting about these times. Yeah, so more specifically, I think machine learning is allowing us to amplify the sensitivity and precision of existing analyses. So it could take any analysis that used to be done with cuts or summary statistics, and it can supercharge them by using more information in the event. It can accelerate the process of simulation and inference. So various measurements that would have taken much more effort can now be automated and amortized using machine learning methods. And it can also automate complex and time-consuming tasks, sort of along similar lines. I think more than any of these things, though, also, and that's what I hope to say, to talk about in today's talk, is how these new tools of modern machine learning can also allow us to design qualitatively new kinds of analyses. So we can do things that we didn't think were possible before. And by that, I mean, use much more high-dimensional data, use unbinned data, do things like density estimation in ways with much more power than we could before. So I think it's the opening up of qualitatively new avenues that's really interesting. Okay, and of course the data that we're looking into with these new data telescopes are enormously vast and growing rapidly. So this is a nice infographic I found online comparing the LHC data set in various forms to other real-world data sets like Amazon or Netflix or something. So you could see that the raw data that the LHC is producing through its proton-proton collisions still dwarfs anything else out there. And of course, there's no processor or disk in the world that can record all this data. So we're forced to compress it, not really compress it actually, we're forced to trigger, so we're forced to throw away most of that data. Fortunately, we also have a strong prior belief that most of that data is boring, so we try to keep interesting events, and that leads to these smaller circles here, which are still measured in the petabytes per year. So these are very large data sets. And I think high energy physics, particle physics has been at the forefront of big data for a long time now. And to go along with this big data, we also have exquisite simulations that we can often use just to understand or develop proof of concept or calibrate things on. So we're in a pretty nice and unique situation. And what's, I think, very exciting about the coming, say, decade or more is that I think astronomy and cosmology are going to also be entering this very large data domain regime. So we have upcoming 3 large galaxy surveys, Euclid, Rubin, and Roman, which are also going to be in sort of the hundreds of petabyte regime. And they're basically either collecting data already or just gearing up to start collecting data. And these are going to survey billions of galaxies in our universe, and that's going to be used to do many different interesting fundamental science applications. A little bit further on the horizon is the Square Kilometer Array, which is a multi-continent spanning array of radio telescopes that's going to supposedly going to be recording in the exabytes amount of data, so a factor of 10 or 100 more than anything we've seen before. It's going to be basically taking movies of radio sources, so like 3-dimensional data cubes of radio sources throughout the universe. Okay, so these are very exciting times, I think, for physics, particle physics, and astronomy and cosmology, and we need these machine learning tools if we're going to get the most out of our data. Okay, so what this talk is going to be about are specifically applications of generative models or generative AI to some particle physics applications, then to astronomy. So, okay, so I believe this audience is mostly experts on this stuff. Maybe it's there's some mixture of people here. So I thought I would just spend a couple slides introducing what I mean by generative models and one specific example that I'll be using a lot, namely normalizing flows. So generative AI is basically a way of going from it's an application of like curve fitting, basically. But you can go from this example, superpowered with deep neural networks and many sophisticated tricks, and you could get something like that, right? So that's what's gotten people so excited, is you can make art and literature, it seems, with these tools, or at least you could make things that approximate those things. But at the heart of it, all of these generative models are trying to do something simple, which is to, so given a collection of data points, so you're always training on data, okay? So given a collection of data points that you believe are drawn from some underlying probability distribution, and let's say they're all IID, then can you train a model to basically produce samples following that distribution, starting from some random noise. So, and that model, basically, you could think of it as a map between random noise, which you might, sample from some Gaussian distribution or something, to the data space. So the space of examples that follow this P of X. So the 2 very famous examples are, for instance, ChatGPT is a generative model that's learning to generate words given previous words, right? So it's trained on sort of all of the internet language, and it's trained specifically to do this task. So given some previous words in a sentence or whatever, can it produce the next word? And then it takes that, feeds it back into itself, and then generates the next word, et cetera, et cetera. So it's learning the probability distribution of words, basically, or tokens. And then the other example is that AI generated art. That was an example. So for instance, Midjourney is one of these image generators, and it can generate an image given a caption, right? So it's the same idea. It was trained on all pairs of images and captions that they could scrape off the internet, and then it learns this conditional probability distribution, and then it can sample, then you can sample from that, starting from basically random noise. So these are actually 2 examples of conditional generative models, which will also be an important ingredient in today's talk. So conditioning the output of the generative model on some input, that's how you do it in practice. Okay, you probably all know all this stuff already. Okay, so I also want to mention that, and again, something you probably know, which is generative models are closely connected to another task, which is important here, namely density estimation. So of course, that's the goal of if you have some data, can you estimate the P of X that given a data point, can you estimate the probability density of that data point? And that's closely related to generative modeling, which is given some data, can you generate more samples that follow that distribution? Of course, one doesn't imply the other, or vice versa. So you have generative models that are not density estimators, and you have density estimators that are not generative models, but often they are closely connected. These are just two examples that I'm sure everybody knows about. So we've all done density estimation. I'm sure every single person in this room has made a histogram at least once. So we're all very familiar with density estimation. This is just like a more continuous version of that in one dimension using KDE, kernel density estimation. And there are sort of new techniques powered by neural networks that are allowing us to do density estimation and generative modeling in much higher dimensions. So as you know, like histograms and maybe even KDE kind of don't scale well to higher dimensions, but with the magic of neural networks, we're able to do things in higher dimensions that probably weren't possible before. Okay, so one of the big heroes of today's talk is going to be the normalizing flow. We've been finding lots of nice applications of this idea to our data. So let me just briefly explain what a normalizing flow is. And feel free to stop me at any point if you have any questions. But so here the idea is to build a transformation between your random noise, your latent space, and your data space that's invertible. And if you can accomplish this transformation, then you can run it in either direction in principle. And so if you run it in one direction, so going from noise, mapping it to data, you're doing a generative modeling. And if you go in the other direction, you go from data back to the noise, then you're doing density estimation. So this is a powerful class of density estimators that are also generative models. And of course, but they're not a silver bullet, because to make the map invertible and to be able to train this thing, it's a highly restrictive set of assumptions. Okay, but basically the idea is in order to transform between the two, you can read off what the probability density of the data is by mapping it to the base space, the latent space, and then all of the interesting information basically is contained in the Jacobian of that transformation. And then using this formula, you can so this is the model, basically p theta. This model has some trainable parameters theta. And so based on that, you can actually train the whole thing in a very simple way using the maximum likelihood objective. You can maximize the likelihood of your data under this likelihood model. And you can also compose, once you have one of these maps, invertible maps, you can chain them together to make, that's the standard trick with anything in modern machine learning, is you could stack them to make them even more expressive. So if I have one invertible map, it might be very simple, but if I start to sort of stack them together, I could get something that's much more complicated. Okay, so this is an example of a normalizing flow in action, mapping a two-dimensional Gaussian to this two moons distribution. And you can see the composition of the map. So it's doing it in 1, 2, 3, 4 steps in this case. So it's chaining together 4 of these invertible transformations and if you run it backwards, you Gaussianize the data. So then you take the two moons data and you turn it back into a Gaussian. Yeah, so in this map, like every point is being mapped point by point to another point in the target distribution. Excuse me. Okay, so hopefully you're all hypnotized by that. And okay, so generative models are also powering a lot of the recent developments in machine learning applied to particle physics. So they're basically allowing us to make very fast simulations, often using surrogate models for complex likelihoods. And they're also powering something called foundation models, where you could train a generative model on large amounts of data, usually using some self-supervised procedure, and then that could be applied to many downstream tasks with minimal additional compute. Generative models are a big part of simulation-based inference, especially posterior neural likelihood estimation are all based on using things like normalizing flows. And the thing I'll be talking about today is anomaly detection. So how we're using these generative models to do new kinds of anomaly detection. Okay, so good. So that brings me finally to some physics. So what is the thing that's motivating all of us working in particle physics, or many of us at least, is something called the search for new physics. Okay, so what is new physics? I might have to explain that. So basically there's this thing called the Standard Model, which was established in the 60s, 70s, 80s. This is from the very authoritative source, The Economist. But yeah, so it shows when every particle in the Standard Model was hypothesized and then discovered. And the theorists have a pretty good track record, actually, except for one. I think there's one counterexample here where it was discovered and then hypothesized. See if you could spot it. Yes, the muon. Yes, which has the famous quote, "Who ordered that?" Okay, yeah, so, but otherwise the theorists have a pretty good track record. And as you could see, there was a lot of, its heyday of the Standard Model was in the 60s and 70s when a lot of things were being discovered sort of one after another. And in 2012, with the LHC, we discovered the very last particle, the Higgs, that was also one of the hardest things to discover. And it's a very special particle in the Standard Model. It's the only spin-zero fundamental particle, and it has very interesting and intricate couplings to all the other particles, and it's also the source of their mass. But anyway, this has been both a huge success. It's the theory of all known fundamental matter and interactions, and it fits on a T-shirt that you could buy at the CERN, the CERN gift shop. So that is a huge triumph of theoretical physics. But it's also been our albatross. It's been weighing on us for decades now because we all wish we could find something that goes beyond the Standard Model. And so that's the new physics that we're all looking for. Some new particle or interaction that goes beyond the Standard Model. Now you might wonder, is this a pipe dream? Like maybe there's no new physics beyond the Standard Model. Maybe you're just wasting your time. So in fact, we know there has to be new physics beyond the Standard Model. So it's not a complete theory of everything. So these are the three most compelling examples. These are definite sources of physics beyond the Standard. These are things that the Standard Model cannot explain, definitely. So we know there's dark matter out there. In fact, that's probably the biggest prize of our time, is to figure out what the dark matter is. We know it's out there and it gravitates and it influences the rotation curves of galaxies and lensing and cosmology, like structure formation, but we still don't know to this day what kind of particle it is. Is it very light? Is it very heavy? How does it talk to us, if at all? For a long time, we thought maybe it could be a special kind of particle in something called a supersymmetric model, but that's increasingly under threat by direct detection, non-observation through direct detection, and also collider experiments. So anyway, it's a big mystery, perhaps the biggest fundamental physics mystery of our time. There's also the origin of the neutrino masses. We know neutrinos have mass, but they can't come from the Standard Model. Standard Model actually predicts that the neutrinos are all massless. So that's clearly contradicted by experiment. And finally, it's known that the Standard Model by itself, if you run the cosmological evolution of it, it cannot account for the matter-antimatter asymmetry, the fact that there's only matter in the observable universe. All the antimatter has annihilated away, leaving us with what we see. So yeah, so these are three things that the Standard Model these are three known unknowns that the Standard Model cannot explain. And so yeah, we know that there must be new physics out there, and so it behooves us to search for it in this vast petabytes of LHC data, which is probing a new energy frontier. Okay, so of course the LHC experiments are aware of this, and they've been doing these searches for new physics since they first turned on. And so by now, So this is a table from already probably outdated, but anyway, this is a table from Atlas showing various searches for new physics they've done. Each one of these rows here in this bar chart is a search for new physics that they did and didn't find the new physics. So they set a confidence, they set an upper limit on the say the mass of some new particle. If it was any lighter, then it should have been seen at the experiment. Therefore, it has to be heavier than whatever mass is indicated here. And so, yeah, so there's probably like, I don't know, 50 searches for new physics here. CMS has done, one of the other big LHC experiments, has also searched far and wide. Atlas has other searches. Okay, you get the idea. There's probably by now hundreds, if not thousands, of searches for new physics at the LHC, and they've all come up empty, so no sign of new physics. So it's a big crisis, I think, in our field. And many people are wondering, is there really nothing in the data? So in which case, should we just shut off the machine? Like, what is the machine really for? So I'm not a pessimist, I'm an optimist. And so the thing that gets me out of bed is the observation that all but a few of these LHC searches, like 99.999% of them, are optimized for specific new physics models. So each one of these searches had in mind a particular new physics scenario with some mass of this particle and this coupling and something specific they were looking for. And then so these searches were fairly heavily optimized. And so not finding something tells us that the model they were searching for is not in the data, but it doesn't tell us too much about other models. And there's far more models than that have been searched for. Okay, so we could be just having a bit of a lamppost effect. Okay, and yeah, I think so. Many of us are convinced that there could be vast untapped discovery potential, and that with modern machine learning, we could open up quite a bit more phase space in these data sets, these LHC data sets. Okay, and what we need are more model agnostic searches. Okay, so there have been at least so far two, so there's been quite a lot of community interest in this idea. And going back to like 2020, several of us organized a data challenge, which we called the LHC Olympics, and where we provided people with 3 black boxes in which we'd injected a little bit of anomaly, a little bit of new physics. These are all simulations. But so we simulated a large amount of background events, standard model events, and we injected a little bit of new physics signal into them. And we asked people to develop methods to find the signal. So it was an anomaly detection challenge. So it resulted, there were about 50 people or so that participated in this challenge, and many new approaches were developed, and the proof of concept works, which are also now turning into real LHC searches. The focus in our LHC Olympics was on on low-level features. Okay, so like all the particles in the event, and at more or less the same time, there was a parallel challenge being run, where the focus was slightly different. It was on sort of high-level features of the event, so sort of compressing the event down to a much smaller dimensional set of information, and then looking for anomalies in that way. So both of them, I think, resulted in a lot of new ideas for model-agnostic searches using autoencoders, weak supervision, self-supervision, semi-supervision. Lots of different ideas were proposed. So that's what I'll be telling you a bit about a couple of these ideas in today's talk. Okay, before I get to the actual method, I thought I would start, especially like for a non-physics audience, with a simple toy model. Okay, so suppose this is your data, and in fact, suppose somebody is kind enough to hand you two buckets of data, two-dimensional data. So each of these points here is like, think of it as an event at the LHC, a collision event. So they're all independent of each other. And suppose someone's kind enough to hand you one bucket of events that they tell you is just background. And for us, background is standard model. So boring old standard model that we hate. And then the other bucket is the data that could have new physics in it or not. So can you, well, okay, they don't tell you how many anomalous events there are, but I tell you there's 200 anomalous events here. Can you spot them? Anyone see them? The resolution of the projector might not be good enough. No, but you can't really see them. So even 200 out of, so what is that actually? It's good to quantify the significance of that, right? So that's just using Poisson statistics, that's roughly 2 sigma, we would say in particle physics. I know I'm speaking to an audience of statisticians, so just forgive me for saying everything wrong if that's what I'm doing, but just, yeah, hold your nose for the rest of the talk. Anyway, so that's roughly 200 over square root of 10,000 is about 2 sigma. So that's how statistically significant the initial anomaly is. Of course, yeah, if you just look at the scatter plot, it's hard to see them by eye. If you do a simple form of density estimation, like a 2D histogram, then that's a nice way to represent the data. And you see very clearly that there's an overdensity here, a bright spot. Those are the anomalous events. Okay, so of course, this works in 2 dimensions where you could visualize things. But how do you do this in higher dimensions? You need some kind of automated procedure to find this like region of interest and to select the interesting anomalous events. So yeah, so the question is how to develop a procedure that works, in a case where you can't necessarily visualize everything to select these anomalous events. Okay, and so many of the approaches we've been developing are based on this idea of this anomaly score, so which is actually a likelihood ratio between the data density and the background density. And I guess the statisticians in this audience are very, very familiar with this idea of comparing 2 densities, so likelihood ratio basically. And intuitively, what you're doing if you look for events that have high anomaly scores, you're looking for places where the data is overdense relative to the background. And if you dig into it a little bit more, you could actually show, so the form of our data density is a mixture model between the background and the signal. So it's mostly background. Epsilon here is very small and a little bit of signal. And you could actually then easily convince yourself that by taking this ratio, the anomaly score is just monotonically related to the Neyman-Pearson signal to background ratio. So if you really could estimate this thing well, you would have the Neyman-Pearson optimal anomaly detector for any unknown signal. So that's the crux of the idea here in a nutshell. So we're all trying to come up with ways to estimate this anomaly score as best as we can. Okay, so there's sort of 2 approaches to estimating R of X. I feel like I've been talking for a while, so if anyone has any questions, feel free to slow me down. No? Yes?
What happens
Thanks,
if
Tay.
your background is your data, like if you use the left-hand side of the right?
If the
Use the right plot on the left.
Use the right plot on the left. Right plot on the left. Right. Yeah, then ideally this would be 1, and you wouldn't find anything interesting.
Right. Could you find your training data or your data?
Could you find the anomaly if the training data was the data? Yeah, so I think you'd, not using this approach, you need some kind of reference sample that you believe is background only. There are other approaches maybe to find the anomaly. Yeah, not with this approach. Yeah, good. Okay, so yeah, there's 2 main approaches I would say to trying to estimate this anomaly score. One I would call direct density estimation, where you try to train density estimators on the data and the background samples and separately learn these 2 likelihoods, these 2 probability densities, and then you just take the ratio by hand. The other approach is actually more powerful. It goes, we call it the likelihood ratio trick. Was there a question? Oh, okay. Yeah, so the likelihood ratio trick is basically to turn the Neyman-Pearson lemma on its head. If you train a binary classifier to distinguish data versus background, then you could actually approximate this likelihood ratio if your classifier is close to optimal. So that's the other approach to getting at this. Okay, so good. So here's how it would work in this toy example. So here I trained the direct density estimation method using some Gaussian mixture models to get R of x, and then I select the events that have elevated R of x, and I could see now it's selected the anomalous events, automatically without me having to look at them by eye. Okay, it's also not perfect. There's some noise here that you can't see, and that goes back to the fact that we can't ever really learn R of x perfectly, but we can only get some approximation to it. Okay, good. So how do we evaluate how well we're doing? So we want to win somehow, right? So we want these anomaly detectors to improve our situation. And so the way we think about it is, so after a cut on this anomaly score, like the previous example, we had a cut of 1.2, we're left with hopefully a purified sample that has much more signal relative to background than we started with. And so we think of this in terms of some efficiencies for the signal and for the background, some multiplicative efficiencies. And then we think of the initial statistical significance of the signal as being enhanced by the cut of the anomaly score, and it's enhanced by a multiplicative factor. So the signal efficiency divided by square root of background efficiency. And so we call that thing the significance improvement factor. And so basically, if that number is bigger than 1, we are enhancing the statistical significance, naive statistical significance of our anomaly, do it by doing all this fancy anomaly detection. Okay, so like in this example, for instance, in the toy example, you could see how the significance improvement, it's a function of the cut. So it's a function of, say, the signal efficiency, and this is what we call a SIC curve. And so the classifier-based approach and the density estimator-based approach are shown here. You can see the classifier-based approach outperforms, and it peaks at a value of about 7, which, just to put that, what that means is that if we started off with an initial 2 sigma anomaly, we could enhance it with these techniques to something like nominally, 14 sigma, which of course doesn't. There's no such thing as 14 sigma, I guess, in real life. But yeah, that's what it means nominally. Okay, and in case you're not familiar in particle physics, our threshold for discovery, somewhat arbitrarily, is 5 sigma. So if this were medical physics, then, if this were medical science, then we would stop here. We'd already have something statistically significant at 2 sigma, and we should stop the drug trial and give everyone drugs. But in particle physics, we wait for 5 sigma. So that's what all of this is about. Yeah, how can we turn a small anomaly like 2 sigma into a big anomaly that's more than 5 sigma? Okay.
What is significant improvement?
Okay, good. So thanks for the question. So yeah, so this is what I was trying to explain here is that after we cut on the anomaly score, the number of signal events and background events change by some efficiencies, some multiplicative efficiencies.
Is it reconstruction?
It is, so no, so like, let's say I had, okay, in the example, this toy example, I had 200 signal events. And if I do a cut, I don't know the exact number, but let's say I'm left with 100 signal events. So then my signal efficiency is like 50% in that case. And maybe I started off with 10,000 background events and I'm only left with 1,000 background events after the cut. So my background efficiency is 10%. That makes sense? So that gives me these two factors, and then the amount that my significance, which is s over square root of b, changes by is this multiplicative factor shown in the circle here. So that's the amount, the multiplicative factor by which the s over square root of b significance is enhanced. Does that answer your question? Okay. Good. Okay, so the last thing I'll say maybe is, so in practice, maybe this was what Tay was getting at too, is that we don't have access to perfect background samples, so nobody is kind enough to hand you this bucket of pure background events. You have to work for it. And so you either need simulations to get that, simulated standard model events, and generally our simulations are very good, but we don't trust them enough to get 5 sigma out of them. So we usually resort to control regions derived directly from the data. Okay, and sort of one very successful strategy that we've been pursuing, which sacrifices some model independence, is to build on this idea of the bump hunt. Okay, so I don't know how many of you are familiar with bump hunts. But okay, so I see some nodding heads. So yeah, so this bump hunt strategy has been used to discover many fundamental things like the W and Z bosons and most recently the Higgs. And the idea is to assume that the thing you're looking for is localized somewhere, usually in one dimension. Okay, and for us it's usually the mass. It's called the invariant mass. It's the mass of some particle. And then you posit that and you eventually have to slide this window across to search for the new physics everywhere. But so for any given window, you assume that the anomaly is all in here, and so the sideband regions don't have any signal in them, and you can use them to get your background estimates. And so yeah, so we learn the background in the sidebands, and we could do this now in more dimensions. We could do this in very high dimension if we want, using generative models. And then we can interpolate the background in the sidebands into the signal region and get an estimate for the background density or the background generative model in the signal region. Okay, if that's a lot to digest, here's like a cartoon of that. This is what we have in mind. So we basically want to learn the conditional density here in the bump space, in the bump feature, and then we have some additional features where we're trying to find the overdensity that's happening here. So if you like, this two-dimensional X is like what I had before, and we're using this bump feature to give us background regions and signal regions in the data. Okay, so yeah, so this is the interpolation step here showing, so if we can learn the probability density conditional on M shown in red, then we could sort of hope to interpolate it into the blue region. Okay. All right, how much time do I have?
You have about 10, 15 minutes.
Okay, so let me just rush through this slide then. So these are different ways that we've come up with to do this interpolation, basically. Starting with, so this is the idealized anomaly detector. This is if you had perfect background samples. So that's one of the reference points that we compare against. And then so one of the original ideas for how to do this goes back to 2018, 2019, work of Ben Nachman and collaborators, which said, let's not do any interpolation at all. Let's just classify the sideband data against the signal region data. So no interpolation at all. And that works if the sideband data really looks the same as the signal region data in all these features, which is can be a strong assumption. Okay, but when that assumption is true, then this idea of koala hunting or classification without labels, bump hunting, works very well. Then what we came up with in 2022 is a way to do the interpolation so that you don't have to assume that all the distributions are the same in the signal region and the sideband. So here we fit a normalizing flow, learn the conditional density, do the interpolation, and sample from it in here. And then we could train a classifier to tell the difference between the data and the synthetic background events. And we could use that to get the anomaly score. So we called that classifying anomalies through outer density estimation, or cathode. And before that, actually, Ben and I did the same thing, but using the density estimation approach. So we train a density estimator out here, we train a density estimator in here, and then we take their ratio after some interpolation. So that we call anomaly detection through density estimation, or anode. Okay, so this is the likelihood-based approach, and the other ones are classifier-based approach. And then we're all developing these proof of concept using some simulated LHC data. So if you also want to play around with this, I highly recommend you check this out. This is the R&D data set from the LHC Olympics, where we simulated 1 million QCD events. These are the standard model background. And we so we produce some BSM signals, which consist of anomalous events with anomalous jets. And we also, so we kind of use our physics knowledge here, again, losing some model independence. We could specialize to a set of high-level features, so just a 4-dimensional space for our X, and do the anomaly detection in that space. Okay, so that makes the problem much more tractable. Okay, so here is a plot of the features. So let me just skip over that. But you can see that the new physics signal is localized here in this window in the invariant mass, and it looks quite different relative to the background features in all these four different variables. So these are two invariant masses. Sorry?
Like you have X and Y. Like, can you give example like X, Y have different X?
Yeah, so these are all like beyond the standard model hypothetical particles. This would be a Z prime, something like our Z boson. X and Y would be just two heavy scalar resonances, which we arbitrarily gave them masses of 500 GeV and 100 GeV. So we just came up with this, out of thin air. This is an example of one specific model that you could be searching for. Yeah, but the goal here is to develop like a model independent or somewhat model independent method way to find this model. If that makes sense. Like if I knew I was looking for this model, I would just train a supervised classifier on samples from this model versus the background and be done. So the goal here is to not do that and still find the model. Yeah, so that way the technique would have broader applicability. Yeah. Okay, so here's the plot of what we're doing, the significance improvement. Shown here is like the fully supervised baseline, which is the best you could ever do. Shown here is the idealized baseline, so if you had perfect background samples. And you can see that cathode is basically matching the idealized case, which means the synthetic background samples that are coming from cathode are nearly perfect as far as this is concerned. And so we can enhance an initial 2 sigma anomaly by up to 15 times, factor of 15 using cathode. So that would be, a huge improvement in the significance. Yes, Iris.
So, like, quick question. But for these methods, you have to specify what the signal region is by hand?
Good. So yes, so we're doing a sliding window strategy, like a 1D bump hunt. So yeah, we're sliding this from here to here. Yeah.
Yeah. And the width is.
Well, the width, yeah, that's another parameter which in any proper bump hunt you would usually pick a few values like a narrow width and wider search. So that could also be done here. Yeah. Yeah, good. Okay, so yeah, so that's the sort of the power of these approaches is that they're able to enhance small anomalies to big ones, just like in that toy example I showed. And again, you could see how anode, the likelihood-based approach is not performing as well as the classifier-based approaches. That also is something we see here. Okay, so in case you're wondering how you would actually turn this into a proper discovery, so it's not enough just to be sensitive to the signal. You also need to get, a p-value out of this. So you need an accurate background estimate. And so the strategy we all envision doing is to cut on the anomaly score, and after that, do the traditional 1D bump hunt in the invariant mass. Do the background estimations from the sidebands, and then do basically a counting experiment in the signal region. Okay, and so a key point here is that these methods should then be robust in the sense that the anomaly score you get might not find any anomalies, but it shouldn't produce any false positives, ideally. So that is to say, as long as we're getting our background estimation and p-values in some orthogonal independent way, we could be suboptimal, but hopefully not wrong. Okay. All right, and so just recently, this was finally, after several years inside CMS, cathode was turned into an actual proper CMS search done on real data. It didn't find anything, unfortunately. But anyway, it sets some interesting limits on many different models because it's model agnostic or somewhat model agnostic. And yeah, it's the first, I think, of many new searches that are going to be done this way. Okay, so in my remaining few minutes, maybe I'll pivot to astronomy, unless there are any questions about the particle physics side. Or we could talk afterwards, I guess. Yeah.
For those model limits, wouldn't supervised searches use this method?
Yeah, so given any model, the supervised search would be the best, yeah.
So if you're gonna put limits on those models, why wouldn't you just do the supervised search and all?
I mean, this is a thorny philosophical question, yeah. So how do you It's actually an interesting research question maybe, is there a way to report your results, null results of a model agnostic search that doesn't involve setting a limit on something concrete? If there is a way to like say how well you've covered the parameter space in, more broadly than specific models, then, that would be a new way of reporting the results, which I think would be a big deal. Yeah. So no one could come up with such a way up till now. So we're stuck with setting limits on specific models, which is how we've been keeping score at the LHC for, or in collider physics for forever now. Yeah. That probably answers your question. Yeah. Yes.
So about this coefficient that you mentioned, I forgot how you call it, this efficiency coefficient.
The significance improvement.
Yes.
Yeah.
So that one means that you know what is your signal, right?
Mm-hmm.
What if you don't know? Because in our data we don't know.
Indeed, yeah. So the whole strategy here, probably wasn't very clear, is we're developing all these model agnostic strategies and we're proving that they could work on specific signals. So just as a proof of concept. And ideally you could test, 7 different signals to see that I could find them all. We didn't do 7, but we did like 2 different signals actually, at least. So.
But this will be true in this Olympics and in this dot, right? But in the CMS analysis.
Indeed. So that actually, so that's a good example. So CMS analysis, they set limits on maybe like 10 different signal models, and cathode was not the top performer in several of these. So so the
signal there is they know already which signal they are searching, and then they do the position.
Yeah. So the philosophy is that we develop this model independent search strategy. We do the search, we don't find anything, and then we got to set limits on something to report a result. So then they pick a few models to set limits on, just to show that, like, the fact that we didn't find anything still gives us some information about, nature. Does that answer your question? Yeah. Okay. Yeah. So actually, there's many different approaches here, not just cathode, and there's lots of interesting complementarity between the approaches. Some are good at finding some signals, and others are good at finding other signals. Yeah.
So thinking about cathode nano, it's not really completely model agnostic, right? You have some high dimensional space.
Yeah.
In your Olympics, and you have to you pick some special projection of that space.
Exactly.
To do your scan.
That was this initial proof of concept, and then that's what got turned into a CMS search. Mm-hmm. And I guess, I could show you in the backup slides if we talk later. We're also working on ways to expand this to more features, so make it more model agnostic. And the holy grail here would be no compression at all, just feed it all the particles in the event, and it can find basically what the interesting high-level features are. And that's a much harder problem. You have to have a generative model that can do much higher dimensional phase space, and it has to be not confused by uninformative, noisy features.
But you still need a special variable to get the background?
Yes, so then you're always left in these approaches, this resonant anomaly detection with the assumption that, there's one feature where it's resonant in. Yeah.
So can you extend this to non-resonant, or is that?
So we do have one paper on that so far where we're thinking about ways to do that. I mean, you still need a way to get the background somehow. Mm-hmm. And so like if it's a jets plus med search, you could maybe do like gamma plus jets as your control region, or and Mikhail was telling me today about things that they're doing with, or I don't know who. Oh, okay, yeah, good. So I think that's also interesting. Yeah.
So we have about 5 minutes left, so maybe let's save the rest of the questions to the end, and we do like a 5-minute version of that.
Yes. Okay. Sorry. Yeah. So I did want to tell you about how we're also applying these same techniques to astronomy data. And here we settled on searching, or we realized we could, so I was interested in these things called stellar streams for a while now. These are interesting objects to study in the Gaia data. So Gaia is a space telescope that's out there at the second Lagrange point, launched in 2013, and is cataloging, basically making the most complete catalog of Milky Way stars ever made. And it's recording not just where they are in the sky, but also their proper motion, so their velocities on the sky. And so there's no other catalog like this ever made. And by now it's gotten over 1 billion stars with accurate positions and proper motions on the sky. So 4D information. It also records their color and magnitude in 3 different optical passbands. And for a much smaller subset of stars, the closer ones, it can find also measure their distances using parallax and their radial velocities using onboard spectrometer. Okay, so yeah, and so in this big catalog of over 1 billion stars, there are these interesting objects called stellar streams that we're interested in finding. And so here the idea is, so you might have a dwarf galaxy or a globular cluster that's orbiting the Milky Way, and after many, many orbits, it gets what's called tidally disrupted. So it gets stretched apart by gravitational effects and goes from being a compact object to being an elongated stream-like object. And so these are stellar streams. And the reason that they're interesting to us is that they are thought to be unique astrophysical probes of dark matter. So because they're very loosely, they're not really bound to each other anymore. They're like people that all happen to be going in the same direction. They could be easily perturbed by other things. So in this case, what we're interested in is a clump of dark matter, what we call a subhalo, that could pass through one of these streams and leave some kind of imprint, like a gap or a kink. So these are some examples of simulation studies people have done trying to explain various features in a known stream, a well-known stream called GD1, showing how a clump of dark matter could have produced like this gap here and this spur, they call it, feature there. So yeah, so it's believed to be one of the few ways we could actually detect one of these small clumps of dark matter. And that could be used to test different models of dark matter, like is it warm dark matter, cold dark matter, self-interacting, fuzzy. So there's lots of different models of dark matter that could potentially be distinguished using this kind of information. Okay, so by now there's about 100 known stellar streams in the Milky Way. And many of these have been discovered in Gaia. And many have been discovered using automated techniques, but these automated techniques all assume basically are model dependent. They assume a Milky Way potential, they integrate orbits and look for stars along the orbit. Okay, so we were interested in doing something model agnostic, like maybe we don't know what the Milky Way potential is exactly. And so we realized though that this is actually a resonant anomaly detection problem. In the following way, so here's an example of a real stellar stream showing you how it's localized in position, it's localized in proper motion, because all the stars are moving together. It's also localized in color and magnitude because of astronomy. So they're supposed to lie on something called an isochrone. So it's really a localized overdensity on a smooth background in multiple features. And so this is really ideal for this resonant anomaly detection or enhanced bump hunting. And so our strategy was to choose one of the proper motion coordinates as a resonant feature, and then use the other 5 coordinates as our X features, and run basically train normalizing flows on this data and learn this anomaly score. This being astronomy data, we could actually do this ourselves. We don't have to hand off our method to the experimentalists and then wait 3 years. We could do it ourselves and wait 3 years. Okay, so here's just a brief illustration of how it works on a real patch of the sky. This is real Gaia data centered on some place where GD1 is known to exist. And then you learn the anomaly score. So for GD1 is so well studied, it's got truth labels. So the astronomers have labeled stars as belonging to GD1 or not. So this is like our signal R&D model that we could test things out on. And so you can see how the anomaly score here learned to place the GD1 stars at a higher value than most of the background stars. And so if you do a simple cut on that anomaly score, just like in our toy example, you find what survives looks like this. That is GD1. So it's a stream in position, it's localized in proper motion, and it's not on an isochrone, but it is localized in color and magnitude. The color and magnitude in Gaia are not very precise. Okay, so the method really works, and we didn't have to assume anything about the potential or fit it to an isochrone or anything like that. It just finds overdensities. So yeah, basically we've applied this now to the whole sky. We use a lot of NERSC supercomputing time and train thousands of normalizing flows. And so we apply this to the whole sky, and these are all the stellar streams we think we found that we believe are significant. And it's not statistical significance, but we've studied sort of simulations to try to quantify our false positive rate. So we believe these are more significant or distinctive than anything found in our false positive simulation-based studies. So that's the best we could do right now, and we're pursuing various follow-up studies to confirm this. And yeah, if even half of these turn out to be real, then we've sort of increased the number of streams in the Milky Way by 50%. So I think that's sort of the exciting thing and then maybe some of these will be useful for studying dark matter. That would be the ultimate goal. Okay, so I'm afraid I've gone over time. So let me just skip all that. Hopefully the slides will be posted somewhere. And yeah, I think we're in very exciting times. There's a lot of new data coming. Gaia is going to have a new data release next year, hopefully. And HLLHC, all these cosmology experiments, I think these are very exciting times. And from the stuff that people do here, I think also very exciting times here as well. So thanks.